Okay, I'm going to solve a problem here involving the trajectory of a ping pong ball. If you need your ASMR fix, here we go. There you go. So the ping pong ball is traveling upward at an angle of 30 degrees from the horizontal toward the right with a velocity of 15 meters per second, rotating clockwise, which is conventionally known as topspin, at a rate of 1,000 radians per second, which is actually possible, believe it or not. And you're given the parameters of the ping pong ball, and then we need to figure out the lift and drag forces on the ball's horizontal and vertical accelerations, and then the ball's position and velocity 1.1 second later, and then we're going to determine the full trajectory of the ball, making any necessary assumptions. I'm not going to go through that whole thing, but I will talk about how you would do that, okay? So let's go to our work here. Okay, so the basic idea, let's get our ball drawn in here. We have a ball, and relative to horizontal, which is here, the ball is traveling upward at an angle of 30 degrees, okay? And so this is where you want to be the ball and see the flow, okay? And so given that the ball is traveling upward at 30 degrees, that means that the drag force is going to be exactly in this direction, okay? So this is going to be our F sub D. And now the other thing that we'll have is a lift force, okay? And, you know, if you know that this ball is going upward and toward the right, and it has topspin, you know, if you know sports, you know that that is going to be angled downward. But remember, we had this little rule that we just learned where we can think about the cross product of the minus the cross product of the velocity vector of the object crossed with the omega of the spinning ball, okay? And again, the spinning ball is spinning clockwise like that, okay? So if we take that, just take a moment to do the velocity of the object, which is up and toward the right. The rotation vector is actually into the page. Cross that, you would get a force kind of up and to the left. We take the minus of that, and then we would get that the lift force is going to be like this, okay? So at least we have the directions of the drag and the lift force. We don't know the magnitudes yet, okay? So we're going to be heading towards using this graph over here on the right. A couple things we need for this. One is the Reynolds number, and we can't do anything if we get a wrong Reynolds number. We just are going to check and compare to this Reynolds number, which is 6 times 10 to the 4 for this chart. Hopefully it's close. And then we're going to figure out where we are on the x-axis for this chart to get our drag and lift coefficients. Okay, so let's do that really quick. So I think I'm in the interest of not going super slow here, I think I am going to just kind of write out the calculations and then leave it to you to punch these into your calculator. So I got a Reynolds number, well, I guess I will write this one out just as a warm-up, 15, the diameter of the ball, and then viscosity is in the denominator, 10 to the negative 5th. I actually got a Reynolds number of 5.7 times 10 to the 4, which is amazingly close to 6 times 10 to the 4. It actually never works out this way, and I'm kind of surprised. I swear I didn't rig the numbers, but that would actually give us a lot of confidence that this chart was correct for this problem, okay? So we're in good shape in terms of the Reynolds number. The other thing that we want to calculate is the x-axis, which is, I call it omega star, but you can call it whatever you want. Omega d divided by twice the velocity of, in this case, the object. I call it v, the chart calls it u. If I do that, I get a value of about 1.3, okay? So from that, we can immediately go to this chart and try to pick off the drag and the lift coefficients. I don't know if I can write on here. Oh, awesome. So 1.3 is about there, so I pulled off a lift coefficient of, I called it 0.3. I'm sorry. It looks like it's higher than 0.3, but I'm going to call it 0.3 for the purpose of this calculation. And then for the drag force, or the drag coefficient, I used a value of 0.55, which actually looks pretty good. Okay, and keep in mind these are drag force and lift force. Once we have these coefficients, we can multiply through by the denominator like we usually do for the drag force. The denominator is the same for each one of those coefficients. For the definition, the reference area is the circular area of the circle that the flow sees, or that this, and so applying that is super easy. Okay, so I think I'm going to fast forward through that step. That step, we would say that CD is equal to 0.55, and applying the definition of the drag coefficient in the correct reference area, I got that the, and I'm going to write this like this, the magnitude of the drag force is 0.084 newtons. I hope I did that right. And similarly for the lift force, we had a coefficient of about 0.3. I think it could be argued that it could be a little bit higher than that. The magnitude of the lift force is going to be 0.046 newtons. Okay, so those are the magnitudes. Okay, and now we need to actually link that to the trajectory of the ping pong ball and its acceleration and its velocity, etc. Okay, so that is the question for letter A. Okay, so that does this one. Now we say at this instant, that's important, estimate the ball's horizontal and vertical accelerations. Okay, so for that one, we are going to go back to Newton's second law. Okay, and so in the x direction, we're going to say that the sum of the forces in the x direction is equal to mass times acceleration in the x direction. And we're going to say in the vertical direction, which I'll call z, sum of the forces in the vertical direction is equal to mass times acceleration in the vertical direction. And so I've drawn in the drag and the lift forces. The one force I didn't draw in is gravity, which is, of course, going to act straight down and be of magnitude mg. Okay? So those are the three forces acting on the ball, and now what we need to do is break those forces into their x and z components using trigonometry. And I guess just to be crystal clear here, I am calling z is positive upward and x is positive toward the left. Okay? Okay, so let's do that really quick. It just involves using that angle of 30 degrees, and if you do that for the x direction, you will get that minus the drag force. I guess I'm just going to call it Ft as opposed to absolute magnitude of Ft, but hopefully you get the idea. Cosine 30, that is the drag force in the x direction, plus FL sine 30 is equal to mass times acceleration in the x direction. And just to show you what I'm doing there, I am breaking this guy here, up here, this drag force, into this component and this component here. Okay? So using trigonometry, and you can see that there's a downward component of drag and a leftward component of drag, right? And that's why we have a minus sign for this drag term in the x equation. Now the y equation is pretty similar. It has the additional term of gravity, but almost the same. Fd sine 30 minus FL cosine 30 minus mg, don't forget gravity, unless you're playing ping pong on the moon, in which case you should use a reduced gravity, is equal to mass times acceleration in the vertical direction. I guess just to reiterate, this lift force up here, notice that it has a component toward the right. That's why we have a sign here in the x that is positive to the right, and it's also downward, which is why we have this minus sign here for the z equation. Okay? And I'm going to just quickly provide you with the answers I got for that, which was the acceleration in the x direction is negative 18.4 meters per second squared, and the acceleration in the z direction is negative 40.1 meters per second squared. So let's think about, are those reasonable? So acceleration being negative in the negative in the negative x direction, in the negative x direction, that seems reasonable. I guess drag is, almost double what lift is. And so that the x component of the drag overwhelms the lift force. In the vertical direction, we have lift acting downward, we have drag acting downward, and then we also have gravity acting downward, and all those lead to a very negative acceleration. So it's accelerating at almost 4 Gs, 4 times gravity with 40 meters per second squared in the downward direction, which is a lot, right? So the fact that the ball has the spin and the drag actually is really making it accelerate downward fast quite quickly, okay? All right, so that is letter B. Now let's go up here to letter C. Estimate the ball's position in velocity 0.1 second later, okay? So you want to choose a time interval that is going to allow you to capture how this thing is moving, and that's why I did 0.1 seconds. And then that will lead us into the trajectory of the ball, okay? So for letter C, let me sketch out a new ball here. We have our ball here. This is our initial position, which I'm going to call x0. And it's moving at 30 degrees, and so we might say that, okay, it's going to end up somewhere over here, okay? And just to write in some positions here, let's call this x0 and x1, and then this would be z0 and z1. And of course, we have our initial angle here of 30 degrees, right? Like that. And it's traveling in the upward direction like that, okay? All right, so how do we actually calculate the trajectory of this ball? Well, we're going to use our usual projectile equations, okay? And you're probably used to seeing that where you get a parabola for an object that you shoot in the air if there's no drag and lift. And now we're going to get modified parabolas because we have drag and lift. And it's really kind of cool. You can show the effect of drag and spin of the ball on the trajectory of the ball's flight. And you can answer questions, things like, if you have how much farther will the ball go if you have backspin or topspin and all sorts of fun stuff, okay? So how do we do this? Okay, well, let's work on the positions first, okay? So for the positions, we would say something like this. Our x1 is equal to our original x, and now we're going to use the projectile equations. We're going to say it's going to have moved some amount v naught x delta t related to its initial velocity, and it's also going to have a position that's going to be slightly modified due to the fact that it's accelerating in the x direction. In this case, that acceleration is negative, right? And similarly for the z1, we would say that we have some initial position plus the vertical velocity that it started at, v times delta t, plus 1/2 times the vertical acceleration rate at the 0 time times delta t squared, okay? And that's essentially integrating Newton's second law forward in time to get the position. And if you do that, what I found is that x1 is equal to 1.21 meters if we choose x0 and z0 to be 0. And then z1 is equal to 0.55 meters, okay? So that's sort of showing you where this thing is in space 0.1 seconds later. And I guess very quickly, does that make sense? Well, it was initially moving at 15 meters per second at some angle of 30 degrees. If there was no drag, in terms of the absolute position change, it would have changed by 15 meters per second times 0.1. That would be 1.5 meters, right? And this is the x component and the z component, which seems pretty close to 1.5, right? That's not the x. 1.5 is not the x position. It's the absolute change. Anyway, I think these are right. So that is the position. And now let's do the velocities. These are actually really important to the trajectory. So for the velocities, we, of course, change colors to be blue. And we get v1 is equal to v0 plus, this one is actually simpler, acceleration from that time step in the x direction times delta t. Sorry, this is v1x and v0x. And then we have v1z is, come on, dude, get it right here. Doesn't look like a z, it looks like a 2. Blue, 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 you're my boy. There you go. Okay, v0z, okay, sorry, a0z delta t, okay? Let me just check the time, 1:20. I got to go to office hours in a sec, so I want to finish this up. And that will give us our velocities at the next time step, 11.2 meters per second and 3.5 meters per second. Okay, so what do we do with this? Well, we think about this. These are the velocities now for this ball, like this. This ball is now moving at this x speed of 11.2 meters per second and 3.5 like that, and its new direction is given by the ratio or the angle that's formed by those, right? So what we want to do is say that this angle here, alpha, let's call this alpha 1 since it's our next one. Alpha 1 is equal to the arctangent of 3.5 divided by 11.2, and if you do that, you get a number of 17.3 degrees, okay? So that means that's our new angle 0.1 seconds later. The other thing that we need is actually the magnitude of our v1. So our v1, the vector, the magnitude of that is going to be given by 3.5 squared plus 11.2 squared. Take the square root of all that, and you get 11.7 meters per second. Okay, and that's really important. So now we're done with this step of the calculation. We know the position at this time step. We know the velocity. We now know the angle at which it's headed. And that's really important because we're going to go back now. And for this ball, I'm going to go ahead and draw here. We have to draw our drag in the direction opposite of motion, right? Relative motion of the flow. We have to draw our lift like that. So this is lift and this is drag. And then we repeat the calculation to the next time step, okay? And ideally what we would do now is we would recalculate that parameter of omega star to get new values of CD and CL. Obviously that's kind of a nightmare if you're trying to do this on a spreadsheet, unless you can somehow write those out in a function. So I think the hope would be that those are not, that the omega star value is not changing too much over the trajectory, that you can just kind of hold CD and CL constant, at least for an initial quick calculation. And then you could go back and check that parameter to see whether it was changing enough that you should actually change it, okay? So that's kind of the whole deal there. And if you plot out the trajectories, you should see a difference between no rotation, no drag. If you have no rotation and no drag, no lift and no drag, you get a parabola. If you have drag, you get a different shape. If you have topspin, you get one shape. If you have backspin, you get another shape, etc. Okay, so hopefully this is helpful.